Okay, I think it works now.
Great. Thank you.
No worries.
All right. How's everybody doing? Hope you're hanging in there. Busy week, I'm sure, for all of you and all of us. Fantabulous. Fantastic. I hope you are all doing well. So I guess things to remind you of: the pass, no pass grade option is due on Cal Central tomorrow. If you want to change that to a grade, I think the default is pass, no pass. So just keep that on your radar if that's something that you want to do. Otherwise, we're working to get back all your labs soon, but it's a busy week for us as well. So trying to do that though as soon as we can. Your exam is on Monday. It'll be open for the full 24 hours starting at midnight until 11:59 p.m. for Pacific time. So hopefully that works out with everybody's schedules. Should be pretty straightforward. It's the same format as your midterm was. And there's only one image on it, and so if you have an issue seeing it, I hear that you're supposed to clear your browser cache, and I'll send out a resource on that because B Courses published something. Okay, so about like how to help solve that problem. All right, so should we go ahead and get started?
I have something to add. For those who have some last minute missing or haven't submitted your homeworks, please reach out to your GSI, either Michelle or me, and we need to coordinate and might offer you extension. But things we need to submit your final grades no sooner than like 2 days after your final. So please make sure you can at least submit all your labs before May 13th. And after that date, we won't accept any like new submissions because we probably already submitted the final scores.
Yeah, so just as Chindan said, just talk to us if you fall into that category. Cool. Okay, anything else, Chindan?
I'm good.
Okay, so we'll go ahead and get started. We're gonna toss it to you guys to see what you want to talk about, and then we'll go from there. So you can either just shout it out on your microphone or type something in on the chat.
And the final is 3 hours.
Oh yeah, you'll have 3 hours.
I guess I'll start. I'm looking at number 4. Why do deserts tend to form at mid-latitudes?
Yeah.
I remember we went over this briefly, but didn't go into like a ton of detail. Something about like cells.
Yeah, so the Hadley cells at the equator. So what happens is you have the rising of hot air at the equator, like right at 0 latitude. And what that does is it causes the uprising of moisture-laden air, but then it gets trapped by clouds in that area. And so then as the air continues to cycle through the Hadley cell towards the mid-latitude, so it's going now up towards like the 30-degree latitude, it's dried out because that moisture was trapped in the clouds near the equator in the tropics. And so you have dry air descending at the mid-latitudes, so there's no moisture in it, and therefore it is dry, arid, and produces the deserts
So does it how does it get trapped at the tropics? Is it why isn't it just moving?
Because I think it's the temperature gradient that causes the cloud formation. And so the moisture gets trapped with that temperature gradient.
Thank you. Okay, I guess I had other questions. Moving to number 6, it asks for the 3 factors that produce the Atacama Desert.
Yeah.
I remember one of them is it's a coastal desert.
Yeah. So actually, this one, you caught me. So there are 3 factors that cause the Atacama Desert, and one of them has to do with the cold water stream. And to be totally honest, I didn't have enough time to get into why, for my own brain, why that made sense. So I'm gonna have to do some research right now and get back to you about that. But the others is that it's forming at the mid latitudes, which again for the Hadley cell is what we were just talking about, and then also the rain shadow caused by the Chilean coastal range in that area. But I'm gonna have to do some research and get back to you about that. Why the cold water stream affects is also a factor.
Okay.
Could you go over number 7?
What aspects of ancient sandstone would you study to show that it was originally a desert sand dune? So why we were looking for any sort of factors that would indicate to us that it was a dune. Things that include, this includes things like graded bedding as well as cross bedding. Which is that shift in the directions that we see in the wind direction, as we see in the image here, as well as you would hope that in order for you to identify that the sediment was aeolian or was transported by the wind, often you see that the grains are frosted and rounded due to transport and abrasion. So you'd want to look for those factors in trying to determine whether or not your sandstone was a dune at some point.
Can you specify what frosted means?
Frosted means it means that it has a frosted appearance, like it looks like it's been abraded or has gone through abrasion. So I guess when you take a piece of sandpaper and sand something with it, that's not really, and it gets kind of chalky and white because it's been abraded and it's gone through abrasion. It's that, or even your skin, right? You scratch it and you can see the dead skin flake off. It's that sort of frosted appearance.
Okay, thank you.
Mm-hmm.
I have a very minor correction on question 4.
Yeah.
So Michelle is almost right. So because of the temperature gradients, the air near the surface is more moisture, but when the air going to the higher altitude, it gets drier because of the low temperature. So as you see from the Hartley seal near the mid latitudes, the air is going from the above to the surface, which means bringing the drier air to the surface and just making the desert. So it's not the water getting trapped by the clouds, but the drier air movement downwelling near the mid latitude. Whereas in the tropical area, it's mostly moisture air moving upwelling, so moving from the surface to the above. And as a result, because of the temperature gradient, they will lead to a lot of precipitation and also a lot of cloud formation here. But in the mid latitude, there basically not a lot of water in the air.
So so are those just locations where like basically all the air coming in is descending?
Most, yeah. It will definitely dominated by the synoptic weathers. For example, there might be few days that with precipitation, just like the weather season at Berkeley, but in most of the days it's driven by the Hardy cell, so it's always experiencing the downwelling air.
Okay, thank you.
For number 8, why specifically glacial times would it show that there were, it asks, why does Luss provide evidence that dust storms and strong winds were common in glacial times?
Mm-hmm.
So
This is because, so Luss is this thick blanket of fine grain sediment. And we think with glacial times, as the glaciers are melting, they're along with that melt water in those outwash plains at the foot of the glacier include a lot of fine grained sediments that were entrained in that transport. And when it dries out, and whether that's because it warms up and that outwash plain dries out, what happens is all of those sediments get entrained into this wind and eventually get deposited downwind in these thick sort of unstratified deposits that are these loess deposits, or these periglacial loess deposits. And so I guess specifically for glacial times, it's because of that, because of the very fine sediments that are transported from that meltwater outwash.
okay, thanks.
Mm-hmm.
So for number 17, where it says list 4 factors that control landscapes,
Mm-hmm.
I was wondering for that, would that just be like erosion, weathering, that kind of stuff? Like, would it be rain, or like what specifically is, I guess, looked for?
Yeah, any of those like driving factors. So erosion is one of them. You know, rain would fall under erosion. Things that build our mountains, tectonics. Other sort of activity, like major activities that we see, such as like glaciers, right? They're huge in forming landscapes, carving our landscapes, depending on where you are and what time it is. Any sort of human intervention, biological activity.
Okay.
Like any sort of one of those big factors that could really, carve a landscape.
Okay, thank you.
Mm-hmm.
Could you go over 23, the one where it says need to look this up, not covered in class?
Sorry, is that the Tokyo Protocol? Kyoto Protocol. What were the objectives of the Kyoto Protocols? So basically, it's an agreement among different countries in terms of reduction of greenhouse gases, particularly CO2. So the protocol argued that all the participant countries have their responsibility on reducing the greenhouse gases. So, for example, they issued a lot of treaties on taxing the CO2 emissions in order to control the in order to control the additional global warming. one very little interesting fact that they said all the countries need to endeavor to control or reduce the greenhouse gas concentration in the atmosphere to a level that will prevent dangerous anthropogenic interference with the climate system. So it's a very political-based treaty, but it's still involved with a lot of scientific findings because no one knows what's the threshold level for the greenhouse gases in order to make it not risky for human health. So basic scientists run a lot of climate models and doing different scenarios and to see, okay, how much additional emission per year that we can add into our system in our, but still prevent further dramatic global warming. Yeah. And using that number, the countries get into the negotiation and discuss about what percentage of their CO2 emission reduction in the upcoming years. But that's then a whole it's a much longer story. Oh. So in terms of what were the objectives of the Kyoto Protocol, yeah, I think I covered it. The goal is to reduce the greenhouse gases, particularly to regulate the CO2 emissions.
Could you possibly go over number 27?
Number 27. Extremophiles. It's a microorganism that live under extreme conditions. I don't want to get into the presenter mode. Can you guys all see these text clearly? Okay, I assume you can see these, right? Would that be too small? Michelle?
Yeah, it's good.
Okay, great. Yeah, so basically it's these microorganisms that can survive in very extreme conditions. How to define these extreme conditions is basically the conditions is being very, it's barely observed on a normal global systems. So extreme conditions can include extremely high pressure or extremely low pressure, extremely high temperature or extremely low temperature. And also for some specific ocean systems, for example, the Great Salt Lake, it also includes extremely high salinity. In some other situations, the microorganisms might bear with extremely high acidity. So given different tolerances, you can characterize the extremophiles by different types listed in this table. I asked to name some examples and where they live. Yeah, I think it's basically included in this table.
Thank you.
Could you go over number 9?
Number 9.
Yes.
I really like this question. It's one of my final questions in David's another class.
It's cool. Do you want to talk about it, Gina?
No, we should go. Huh? I already forgot all these equations because I did this class like 1 year ago.
Okay, so explain why oxygen isotopes 16 and 18 can be used as a proxy for temperature, and explain what it's meant by proxy. So oxygen 16, so we're dealing with two isotopes here of oxygen that we see, isotopes oxygen 16 and oxygen 18. We know that oxygen 16 is lighter than 18. So that means that it evaporates more readily than oxygen 18, and 18 will more likely be deposited because it's heavier, right? So it'll stay in the ocean as opposed to being evaporated into the clouds. So, so as we get a lot of our climate temperature studies from Arctic ice. And so as we're moving water from the equator of the Earth as it's being heated up and pushed up into the atmosphere, and as it goes through the various cells on its way to the polar regions, it's being evaporated and deposited each time. And so, okay, you can't see, my mouse doesn't work, but it goes through this sort of distillation process. So, so basically what I think of this delta symbol as a ratio of oxygen 18 to oxygen 16. And so as that del value gets more negative, so like once you reach the poles on the right-hand side of this image, it's a very large negative number, meaning that the oxygen 16 ratio is oxygen 16 is much higher than oxygen 18. So when we're starting off down in the subtropical, oops, sorry, this is mine. We're starting off in this near the equator, and oxygen 16 will be uplifted into the clouds because it's more readily evaporating. It'll then precipitate down, and each time you do this, you increase the oxygen 16 content as you move. Sorry, I'm repeating myself again, but as you move towards the poles, due to this distillation process. So once you reach the poles, most of your oxygen 18 has been precipitated out. That is why our, does that help make sense?
So what would, say like a more negative delta during a certain time period's ice core like mean?
So if it's more negative, it has a higher ratio of oxygen 16, which means that it's colder. Whereas if it has more oxygen 18, it's more likely it'll be warmer.
Okay, thanks.
And we use this as a proxy because it's not a direct measurement of temperature, right? It's just something that we can use to indicate temperature.
It's a very efficient way to identify the paleoclimate.
Just clarifying, you said more oxygen 18 at the poles would mean it's colder or it's warmer? I missed that.
More oxygen 18 would be warmer.
Warmer. Okay, thank you.
Would delta equals 0 be like the ratio in our oceans right now?
It depending on which initial point that you pick.
Okay.
Could you go over number 13?
How do orbital cycles of eccentricity and obliquity affect onset of glacial periods? So basically what's happening here is if over a 100,000 year period, our Earth's orbit varies from something circular to something more elliptical. And if it is following one of these more elliptical paths, it has it receives less radiation from the sun because it's able to get further away from it over a longer period of time. And this reduces the solar irradiation that we experience on the Earth, meaning the Earth doesn't get as much direct heat from the sun, which enables which enables ice to build up and produce a colder climate. This is how we get our glacial interglacial cycles on the span of 100,000 years, because if we're either in a elliptical orbit, which gives us greater time to build up ice and have a glacial period, versus a circular orbit, which prevents us from really having any chance of building up any ice, because we're always within close proximity of the Earth's radiation. Obliquity, the same thing. So obliquity is the tilt of the Earth on its rotation axis. And so, for example, at the equator, where the Earth is most directly able to, it's where we get our highest solar radiation because of the direct sort of angle that that sun's rays makes with the Earth. But as we go towards the poles on our sphere, we hit an oblique angle, which reduces the solar radiation. So obliquity for the same reason, meaning as you increase that angle, the radiation decreases as well, correspondingly. And what is the evidence? And we use the isotopes in glacial ice, in ancient ice, to tell us about this sort of timeline of cycles. So if we, this Milankovitch cycle.
Wait, sorry, I don't super understand why increased tilt would lead to decreased radiation.
Because it affects the way that the sun is striking, the angle that the sun is striking the surface of the Earth.
Okay.
And so if it is head on, like it is at the equator, this is kind of confusing. So forget about tilt for a second and just think about the Earth as the sphere. Then at the equator, you get the most solar radiation, but as you move towards the poles and it gets that rounded shape, you get this sort of oblique angle that the sun's radiation strikes it at, which causes it to be less intense. And the same thing happens. So then your Earth is on a tilted axis that it rotates around. And if that tilt increases, which it does over 40,000 years, alternates, that also affects it in the same way, because you're increasing that angle away from the Earth's radiation.
Shouldn't the, time averaged amount of radiation that each point on the globe receives, remain the same though, regardless of tilt? Maybe I'm not thinking about this correctly.
Maybe I just don't understand your question.
Say I live in Panama or something, and no, Panama's not close to the equator. Say I live in Ecuador. There we go. That one's easy. And there's no tilt at the moment. Then I'd get the sun head on all the time. But yeah, never mind. I'm confusing myself.
Well, just keep in mind that the Earth is already on a tilted axis of rotation.
So going off of that though, wouldn't that mean that when the Earth tilts more and some areas have that more angled, solar radiation, so therefore it would receive less intense radiation, there would be other areas that would have been more tilted that are now receiving more direct sunlight, so it all kind of balances?
Yeah, I see what you're saying. To be honest, I don't know. But I understand where your confusion comes from. Yeah.
Yeah, I don't see how the whole thing with like obliquity does anything other than maybe change which parts of Earth are warmer and which parts are
Mhm.
colder,
Mhm.
I guess. It wouldn't, in my eyes, change the Earth in its entirety.
Yeah, that's what I was confused about.
Yeah, I don't know. Let me look it up. Let me get back to you.
Sounds good. Thank you.
This random website says the seasons become more dramatic, which allows snow to last longer.
Yeah. Yeah, I don't know. I'd have to look it up a bit more.
Yeah, for a specific point on the Earth, the distance to between this point and the sun will change more dramatic if your tilting angle is larger, which leads to a more clear distinction among different seasons. What's the question is asking? Where's that?
Do you also explain the evidence for this a little more? I know you said isotopes, but like, how do we use isotopes to determine these processes? Like, I know you mentioned for oxygen 16, oxygen 18 for the glacial period, but for obliquity, is it the same thing?
I don't know. I'm gonna have to get back to you. In terms of like, how can we tell like the difference between the effects of obliquity versus eccentricity on using isotopes?
Yeah, just
Yeah.
like, I don't see how you could discern one from another.
Yeah.
Completely.
Well, I think it links back to the previous questions that using the oxygenating to identify the paleoclimate. Because if you get the ice core from the same point, from the same location of the Earth, and dating it back to the specific year and using the oxygenating to identify what climate it was, we can link it back to, we can build up the relationship between the paleo temperature and the obliquity of that point. So using oxygenating, you can first build up the time series of the temperature variation, and then using that temperature variation to build up the time series of the obliquity variation.
So I guess for this, would that be saying that like you would see how long this occurs for, and if it occurs for somewhere closer to like 100,000 years, then you would put it more towards eccentricity, whereas if it's like half that time, then it'd be more caused by obliquity, not eccentricity. So you'd look more at time scales while using oxygen 16, oxygen 18 as a comparison.
That should work, but I'm not quite sure how it works because I didn't look it up.
Okay, sure thing.
Yeah, we will get it back to you. I'm sorry for that.
Yeah, that's all good. Thank you.
All right, last thing on the slide. Is precession related to tilt?
Okay, what else?
When students ask on this slide, is the precession related to tilt?
I don't know. I'd have to look it up. I don't know if precession is related to tilt.
What about number 35?
35. So longshore transport and why does they occur? It's a transportation of the sediment parallel to the shoreline. So basically, if you have a bunch of sediment here because of the current, among some, like after some time duration, this sediment will transported to somewhere that is parallel to this coastline. And why does it occur? First of all, you will have the incoming wave towards the shoreline in this direction denoted by this arrow here. So as a result, this waters will bring the sediment on this shoreline to inward. But as you might observe on the beach, that whenever you have the incoming wave current, it will have the backwards as well, like very quickly. So the water is coming into the shoreline and then getting back out. And these backwards will bring the moving sediments from this location back to the shoreline and building up this zigzag pattern of the movement. So as the time goes by, the segments will slowly move from this point back to this point and until end up with this point. So as a result, on a longer time period, you will see like moving patterns like these. What else? Yeah, it's definitely related to the wind patterns because what determines the direction of the sedimentary movement is the wind direction. If the wind is blowing from the north to the south, it's bringing the sediment from the north to the south as well. But if the wind is blowing from the south to the north, in the same way, the backshore will bring, well, even the sediment is moving inward by these waves, the wind will blow it, will making the backwards, moving the sediments along this trajectory. So as a result, it will move like with the same direction of the wind in parallel to the shoreline.
Okay, thank you.
No worries. We probably haven't put this slide to be courses that we would do after this review session. So you don't need to take a screenshot or anything. We will make it accessible to all of you.
Could we go over question 16, where it asks why erosion of a mountain range would lead to further uplift?
So this has to do with isostasy, which is this is I have another slide about isostasy somewhere. With one of the, I forget what question it is. Hang on. with a wood block.
I think it should be number 11.
Number 11, maybe.
Okay. This one?
Okay, yeah. So basically what this is saying is as you remove, explain the process by which erosion in a mountain range can lead to further. So as you're eroding away material, what's going to happen is due to this equilibrium balance that you have as the Earth's crust is floating on top of the mantle, that will cause an equal and opposite sort of recalibration for that piece to be uplifted. So it's like almost like a positive feedback loop.
Is this due to the changing center of mass for the continent?
I don't know if it has to do with the changing center of mass. I think it's it has to do with the buoyant force, which is essentially the mass, but it has to do with the thickness and the density. But it's not that center of mass is changing. So.
Okay, thank you.
Mm-hmm.
So is it kind of similar to like the epirogeny, like glacial uplift analogy, where like you remove all that mass on top and then it gets forced upward?
Yeah. I think that makes sense.
Okay, cool.
Mm-hmm.
Could you explain number 3, the Coriolis effect, a little bit?
So, this is a phenomenon that causes fluids on the Earth's surface, like air and water, to curve as they travel across the Earth. And this is because the Earth is spinning counterclockwise in a counterclockwise direction. So this is why if you see these cells, so the ones at the equator, just either directly north or south, the blue lines are either tilting to the right. Yeah, they're deflected. And in the northern hemisphere, they travel to the right, and in the southern hemisphere, they're supposed to travel the opposite direction, the left. But it's due to the rotation of the Earth in this counterclockwise fashion.
Okay, and then I get that. And then could you explain the difference between the hemispheres? Because like why they would be going in different directions? I mean, I understand that, but why to the left or to the right based on their position?
Yeah, I don't know that.
It's related to the angular movement because the Earth is a rotating planet, so it's taking a rotational objective as your reference will leading to additional force turn, and the direction of that force turn is determined by the right hand rule. If you want, I can pull up the equation for you, but yeah, I couldn't give more specific explanation without that equation.
Oh, okay, yeah.
Let me find it somewhere.
Could you explain a bit why the sky is blue and sunsets are red, number 25?
Okay. So it's determined by the Rayleigh scattering. When when the light enters through the atmosphere, it's experiencing the scattering because there are always some chemical components. There are always particles in the atmosphere, and Rayleigh scattering occurs when the light interacts with the particles with a size smaller than the light. So in other words, it would be the gas component in the air, for example, nitrogen and oxygen. Another scattering that might be occurring in the atmosphere is called mist scattering, and that's the interaction between the light and the larger particles, for example, like aerosols. And that's why haze happens during the pollution. Going back to the Rayleigh scattering, the scattered intensity is inverse proportional to the wavelength, to the force power of the wavelength. I appreciate that the equation might be too small here, but basically you will find I equal to inverse proportional to the force power of the lambda, and lambda is a wavelength. So given the broader spectrum of the visible light, blue light will have a smaller wavelength than the red light. As a result, where blue light will have a smaller wavelength, it will have a larger scattering. That's why when it enters into the atmosphere being scattered, there will be a bunch of, people standing here, there will be a bunch of light scattered away from the direct light path, straight from the sunlight. That's why you will observe that the sky will be blue. And in the same way, if you glance away from the sun, basically you're standing here and facing directly towards this light path, you will observe the sun being red or yellowish. That's because along this light path, all the blue light is already being scattered. All the remaining visible light will be red or yellow. So all with these wavebands with larger wavelengths. So you will observe the yellowish hue if you're observing the sun. And at the sunset, the sun is no longer on top of you, but more closer to the horizon. As a result, the light path will be much longer than it is during the daytime. So when the sunlight enters through the atmosphere, it goes a very long line path before it reaches to your eye. So what you observe is mostly the remaining red light instead of the blue light, because along this long light path, all this blue light is being scattered and removed from the atmosphere. So yeah, that's why you will observe different colors during different time of the day.
Thank you very much.
For number 16, it asks how erosion in a mountain range will further uplift the highest peaks.
Yeah, so Hudson asked this question a little bit earlier. This has to do with isostasy, which is the balance, sort of the mass balance that the crust has as it floats on top of the mantle. And so basically, as you erode away more material, due to this sort of mass balance, it lifts itself up. This is like this. It has to do with isostasy, which is just the way that something is the crust of the Earth is floating on top of the mantle. So increased erosion leads to an increased uplift. Does that make sense?
Yeah.
Okay.
For number 28, when it says describe a negative and positive feedback in Earth's climate system that involves water, do they want like water, or can we talk about ice too?
Anything can be fine. Because both, no matter what format the water is, it always affects the climate. If it's in ice, it will be glacier. If it's in water vapor, it will be the atmospheric feedback. If it's in liquid, it would be, well, it still involves the water cycle. So just pick one or two feedbacks that involving water.
Okay, sounds good. How about number 32? What is bottom water and how does it form?
So bottom water, by its definition, is the lowermost layer of the water, especially in the ocean or in a very deep lake. How does it form? So it's actually, I think I have slides here. 32 here. And it's characterized by this higher density. They say it means if it has a higher density, it's hard to get involved into the convection. So even you have a steep flow from the continental shelf, it can only go down to the depth which the density of the seawater is equal to the density of the flow. In other words, it never reaches to this bottom water because it shares with, it has a much higher density. And also it's characterized by the different chemical components. It will have a, let me check if I didn't, yeah. It will have a lower temperature and also the lower oxygen, but have a very high bromine concentration. The bromine concentration. And how does it form? I actually looked it up from Wikipedia, so I believe it's correct, even though I haven't done a lot of research on that. So it's formed by this partial freezing of the seawater over the Antarctic continental shelf, especially in the Weddell and Ross Sea, produce sea-free ice and residue bromine with a very high salinity and a low temperature. So I assume it's because of the, never mind, I'm making this up. I would just buy these statements that I found from online sources.
Okay, thanks.
Yeah. Is it covered in the lecture?
I think I remember him mentioning something about it, but he didn't go through it for very long.
Okay.
And Coral, to get back to your coastal desert question, I believe, so that the third factor that I wasn't quite sure of, the cold ocean current, what I believe that to be is that it cools the air around that area. The cool ocean current does, and such that it's not able to hold any water. And so it can often accumulate in a fog, but that's as much water as it can hold. It can't accumulate into clouds and precipitate out due to that cold air temperature.
Okay, thank you.
Mm-hmm.
Related to the bottom water question,
Okay.
for number 31,
Yeah.
yeah, what is the role of salinity there?
So salinity relates to the density of the water. So more salinity means there will be the larger density.
Mm-hmm.
And the food with a larger density is more likely to sink instead of upwell.
Okay. Do we have to know, like, I remember vaguely seeing a map of how all the ocean currents like vary in temperature around the earth and like the direction they're going. Should we know that?
I don't think so. I personally never remember that map. I always look it up if I need it.
Okay, thank you.
I would say the one thing that you would want to know, though, is that generally the oceans are what is driving or sort of balancing the temperature across the planet. And so generally from the equator, the currents flow like north in the northern hemisphere, and I think south in the southern hemisphere because of that temperature balance. Yeah, along continents. Yeah, and they form these cells that we talked about, but I guess it's not so straightforward. So yeah, no. I would just know that oceans are a big factor in regulating temperature around the globe.
Yeah, which is a pattern of it. So, one question, Diana asked question 18.
How are oil and gas formed? So, so these are hydrocarbons, and they're formed from a carbon-rich material that then gets is subjected to an anoxic environment, something without oxygen, that produces the hydrocarbon. And so these are source beds, which are basically carbon-rich beds. And crude oil forms at a depth between 2 to 5 kilometers, and natural gas forms at a depth below that because of the higher pressure. What else does it ask? How are these easily recovered deposits produced? So in order to easily recover one of these deposits, it should be in some sort of easily recoverable formation. And these are formed, these are called oil traps. And they form in a variety of ways. Structural, meaning the land has deformed through tectonic activity or faulting, and that has caused a structural trap. Stratigraphic, meaning you have your oil forming underneath an impermeable layer like a shale or some sort of clay material. And the same thing goes for salt domes. They dome up through a stratigraphic sequence and form these little traps on the sides of them. And so these form sort of like pockets of oil that are very easily able to be mined, or what do we call, pumped out of the earth, gathered in some way. And yeah, does that answer your question? Okay, great. Sure thing.
So number 20 asks how coal is formed, and is that not also just like organic matter underground? No, for a long time.
It's it's almost in the same way, instead that coal only forms from the biological sediments, but it's still experiencing the same like process, including the increasing pressure and temperature, squeezing out the oxygen components and leaving very high carbon content.
And coal often is much wetter. It's from a much wetter environment than another source bed that would form oil and gas. So that's why you're always thinking these peat bogs and stuff.
Also wetlands, because only in that environment will have a lot of biological sediments.
How about number 34?
Ha, okay. So it asks what happens to the wavelength velocity and amplitude of waves as they approach the shore. First, it's clear that the amplitude will increase, because in the deep ocean, if you only focus on a fluid in a specific location, it's actually it's moving along the circular orbit. Near the surface, the orbit will be larger, but if you down to the ocean, the orbit will be smaller because the energy will be higher above the surface. And when you get even deeper, the energy dissipated out. So only down to the depths, only above the depths that roughly equal to the wavelength of this wave will experiencing the circular orbit. Below this depth, the fluid will remain still. So with that in mind, you should expect when it goes to a shallower region shown in this figure, also there will be more energy concentrated towards the surface because it couldn't go down to that deep and to drive the fluid at this depth to move. So instead, it will make the fluid near the surface move more dramatically, leading to a higher amplitude. So there's no doubt that the amplitude will be increased. But in terms of the wavelength of the velocity, I think we are still on debating because I just derived the equations right before this review question, and I think the velocity will change. But I just got the reply from the David, and David said he thinks the wavelength and the velocity will remain constant no matter what, no matter it's in the deep water region or in the shallow water region. So I would buy David's answer because, yeah, I think, yeah. But I still disagree with that.
Okay.
Yeah, with the direction, I still think the velocity will increase. Yeah, if you derive it from the wave equations, but in the current state, that's just the wavelength and the velocity will be constant, but the amplitude will increase. Michelle, what do you think?
I'm gonna go with you, whatever you say, Gina. You did the wave equation. I believe you.
But that in David's last email, he said, okay.
I haven't read his email yet. So guys, we've been talking about this because like we don't agree. I haven't read that email, but
because it's actually a very complex math function. I remember in my fluid mechanics class. Well, by the way, it's covered in a fluid mechanics class in civil and engineering, and we literally spent 2 weeks on this question. Because the ocean waves is not a standing wave. So it not only just change with the time, it also change with the distance. So it's a progress wave. And in that terms, you need to use the both continuity equation and the Navier-Stokes equation to describe the movement of the fluid. Yeah, and it includes a lot of derivation, as you might see from my notebook. And my conclusion is when it gets to the shallow water, the wave velocity is actually proportional to the square root of the height of the depth. So when you get even closer, the depth gets smaller, the wave velocity will be smaller. But it doesn't change the wavelength, because wavelength is the instinct property of the wave. Unless you overlap this wave current with another wave, it never changes the wavelength. So with that, I think the period will also increase. But David seems to be disagree with that. We will reach to a final conclusion and put it in these slides. Yeah.
guys, it's so exciting to be in an academic environment because we talk about these things and it's fun to discuss, go back and forth. And also, as
Michelle, I couldn't hear you.
stuff.
Okay, now you're back.
Oh, yeah, I don't know if you heard any of that, but anyways, cool. What else, guys? I think somebody asked a question about whether or not the precession was related to the tilt. What I can gather is that no, they're two different things. The precession is that the precession is the tilt of the Earth's rotation, moving, like rotating around North Pole like a top, and that varies on a cycle of however many years. And the tilt is actually the tilt of that of the Earth's rotation, so not the wobble, but instead the angle that it creates.
Could you go over number 26?
Why is liquid water so important for life? Do you want me to go through all these questions or just the second part?
I mean, I kind of know that like liquid water is important for life because like, you know, we're made out of it and we need to consume it to survive. But yeah, I guess it's more so this second part.
Yeah, your answer is totally correct. So I will just skip the first part because basically, yeah, I think from whatever point of view that you answer the question, is as long as it makes sense, you can get the points. What objects in our solar system do once contain liquid water? It's actually a very popular research topic because you might notice from a lot of news that scientists find the evidence of the water in some of the planets. I put a summary here. So Mars is a very popular planet, and we definitely found a lot of evidence that the water used to exist on Mars, but it wasn't anymore. It isn't anymore. I put one figure. I apologize that I get this figure from one journal paper, but I didn't put the citation here. That's a very big mistake. But basically, this is the region somewhere in the Mars, and they found that there used to be underground ice near this region, and they even quantify how large it is. And also, the scientists use the erosion features, preview channels, cap of the poles, direct population of the brine mine to determine that Mars used to have the water. Besides of Mars, there are also a lot of icy moons. It's basically icy moons will be the satellites, the natural satellite for each individual planets. And specifically for the Europa, I think this is the most famous one. Includes ice. It's a satellite for, damn it, I forgot. Either for Mars or for Pluto, and it's composed of the ice. There are also some comets and asteroids that might contain water, but I couldn't find a lot of findings from these two regions, so I would just buy with that. Going back to the question, yeah, you don't need to cover all these different aspects. Picking one or two that you know very clear will be fine. Does that answer your question?
Yeah, it does. Thank you.
Okay.
Could you go over number 14, carbonate compensation depth?
Back to that lab that we did. What was it? Sedimentary lab. Yeah. So the CCD. Okay. What is the carbonate compensation depth? It is the depth at which carbonate solubility increases such that
We lost your voice again, Michelle. We can't hear you.
Oh.
Okay.
Can you hear me now?
Yeah.
Okay.
Yeah. You
Mine-
stopped at increases such that.
Okay. Good catch, Emily.
Okay. I don't know. I don't remember exactly, but so it's essentially saying like this is basically the level at which carbonate rocks can no longer precipitate. Oh, did I lose you again?
No.
Oh wait, can you hear me?
We can hear you.
I
You're
can.
frozen.
Yeah.
Your
You're
video.
frozen.
Oh, I'm frozen. Okay. Well, okay. So long as you can hear me. Can you still hear me?
Yeah.
Okay. Okay. So it's the depth at which carbonate can no longer precipitate out and instead it dissolves. It's also where the rate of carbonate dissolution is higher than the rate of carbonate accumulation, so that rocks can't form, these carbonate rocks. So this is why carbonates are only formed in shallow marine environments, because they cannot precipitate in too deep. They'll dissolve. Does that answer your question?
Yeah.
Okay.
Hi, which lab was this?
What was that?
Which lab was this?
I think it was the sedimentary rock lab.
Sedimentary. Yeah.
Oh, okay.
We went over this and that as well.
Yeah, in that lab, you need to fill out a very big table to indicating for different type of the sedimentary rock, what environment or what deposition environment that this type of rock might form.
Oh.
And you also have I think there's a question that's like, you found a carbonate rock at a very high depth. Like, what could have happened? And it's like tectonic, it got placed there. It couldn't form there, but it formed in a shallower depth and then somehow got transported. I'm back.
Okay.
Okay. All right. So we have 6 minutes left. I still have questions that I need to get back to people about, which is how we can differentiate between eccentricity and obliquity using isotopes. In terms of can we differentiate between them by looking at isotopic records? Uh-oh. Did I lose you?
No, we can still hear your voice.
Good. Okay. So I still have to get back about that.
And I will clarify the question 34. What does the wavelength and velocity change when it approaches the shore?
Okay. And I think it was Nina, your question about why does the Coriolis effect differ? Like, why does it go right in the northern hemisphere and left in the lower hemisphere? I sort of started looking up at the equation that it seems like it's very complicated. And I don't know, Chindan, if it's like simple and easy to pull up, or whether or not it's just one of those things that's like.
I think it should be
memorize which direction it goes.
What'd you say, Nina?
It always go to the right hand. So if you stand on the in the north hemisphere, it always deviate to the right hand.
Mm-hmm.
And it's the opposite if you standing in the southern hemisphere.
Mm-hmm.
But it actually comes from that equation.
I have one last question,
Mm-hmm.
which is 33. What are marine terraces and how did they form?
Yeah. Do you have any guess on this question?
Sediment buildup?
Yeah, that's totally right. It's a combination of tectonic coastal uplift and sea level fluctuation. So for example, if at some point the sea level is above here, it won't build up the sedimentary deposition up to this level, right? So along this time period, it will building up sedimentary rocks consistent with the sea level. But over the time, the sea level is been changing and also combined with the tectonic coastal uplift. So you will see this pattern of the marine terraces.
So is it like it lifts a little bit, gets eroded, lifts a little bit, gets eroded?
And also it being uplifted.
Okay, thank you.
Yeah.
Could we go over 29 if there's time to?
29. How does the internal structure of the rocky planet differ from that of the gas giant planet? Oops, sorry, I didn't put any figure here. Just list out some key points that you can use in terms of answering this question. First of all, solid surface. Usually effects for the rocky planets, it would be a solid surface, whereas in the gas giant planet, it won't be any clear boundary between the internal structure and also outer structure. So the gas giant won't have any solid surface. The density, gas giant should have a much lower density than it is than the density for the rocky planets, depending on the components, because ice giant planets mostly consist of the gases. So the density will be much lower than the solid objects. The chemical components, gas giant planets were mostly made of the hydrogen and helium, whereas for the rocky planets were most likely to be like silicates or some metallic rocks. Yeah. Now, Also iron, yeah, metallic, iron, the silicate and iron-based internal structures. What else? For the sizes, the gas giant planet will be bigger than the rocky planets, because you should expect that gas is hard to be closer to each other. As a result, even though they retain as a large gas envelope, it can extend it to a very large distance. If this question show up in the finals, you don't need to cover all different aspects. I think listing out one or two will totally be fine.
All right, so any final questions before we wrap it up? All right, so we will post this on Bcourses in the, I forget where we post it. We'll send it out an announcement where it's located, these reviews. It's either in the lab page or somewhere else. And in that announcement too, I'll get back to you about these isotopes. Yeah, I'm having office hours tomorrow from 9 to 11 if you need them as well. So just hope the rest of your studying goes well, and it's on Monday, don't forget. And oh, this is it, guys. Wait, this is it. Well, guys, I hope you had all a really good semester and you learned something. And it's been great getting to know all of you. And I'm sorry that this was all kind of online. It transferred online, but oh well. I think we did. We got through. And so yeah, I hope to see you around. Let us know if you need anything. And please fill out your course evaluations. Those are very helpful. All right. Okay. Thanks, everybody. Good luck.
Thank you so much.
Thank you.
Bye.
Thank you.
Let's just use this meeting room to decide what answers would that be.
Oh my, wait, you're still recording. Wait, turn off the recording.
Oh.